Hey everybody, welcome to lecture 5 on graphs in your course on analysis of algorithms. So we finally get to the bits about graphs, which is what this course is fundamentally about. So the first thing we want to talk about is, why do we use graphs? What's the point of having them? Well, the main thing about them is that they're a representation that allows us to express general solutions to problems, right? So when we talk about solving a problem on a graph, right, we're saying that we've got this collection of vertices, such as the 0, 1, 2, and all that, and edges, which are the connections between the vertices. And you might be thinking, well, what sort of real-world problem involves vertices and edges? And none, right? But that's the cool thing. The cool thing is that the problems are abstract. They're not real world problems, so they stop us from getting bogged down in reality. As an example, there's a problem that we're going to cover in this course called graph coloring. But where it originates is in something called a map coloring problem, which was a problem that originated in the Middle Ages, where cartographers, who are people who make maps, were trying to figure out how best to color a map so that it's easily readable and yet doesn't use too many colors. So how the problem is framed is that you've got a world map, right? So you've got countries on it. You want to be able to easily figure out where one country ends and another starts. So what you do is you color the adjacent countries a different color, right? So if South Africa is blue, you wouldn't make Namibia blue as well, because then it would be hard to see the border, right? So what you want to do is you want to color adjacent countries using different colors. But you also don't want to just have 200 and something colors. This may have been different in the Middle Ages, of course. But you don't want to have that many colors. So what you want to do is you want to find the minimum number of colors that will allow you to do that to a map. And that's a pretty difficult problem. It turns out to be quite a complicated problem to solve. The problem with solving it is that when you solve it, you'll know how to color a map. And anyone who's not a cartographer will just be like, well, man, why do we care? And of course we don't. Now, if we reframe that problem, if we say, instead of trying to color adjacent countries using the same, using different colors, we say, let's convert this into a graph representation so that it's abstract, right? So now we say, okay, we've got vertices and edges, and sometimes I'll say nodes instead of vertices. They're just synonyms, right? I'm saying nodes instead of vertices sometimes. So we've got these nodes and edges, and what we want to do is we want to color the nodes using as few colors as possible, such that the adjacent nodes, meaning nodes that are connected by an edge, don't have the same color. Now that's fundamentally the same problem as the map coloring problem, right? Like, a solution to one is a solution to the other. So all I've done is sort of exchange the nouns. Where previously we were saying countries, now I'm saying vertices. And previously we were saying countries share a border, and now we're saying countries, vertices have an edge between them, right? But fundamentally it's the same problem. I just changed the words. But the powerful thing about changing the words is it makes it clear that we can change the words to anything. Okay, so the most commonly cited use of graph coloring right now is not to color maps. It's actually to organize timetables, things like exam timetables. So if I were to try and set an exam timetable, what I'd be trying to do is to assign time slots to courses such that courses which share a student are not written at the same time, right? Because otherwise that poor student has to write 2 exams at the same time. Now, that is just another noun replacement of the graph coloring problem, right? So if I set up a system where my nodes are courses, and what I do is I draw an edge between 2 courses if they share a student, then if I apply graph coloring on the resulting graph, I'll end up with time slot assignments for my exam. Now, the thing I probably mention the most in my lectures is that computer scientists are really lazy. So this sort of thing really appeals to us because the fact that someone at some point solved the map coloring problem means that we can now construct exam timetables. There's a problem we just don't have to solve. And the only thing better than solving a problem is not solving a problem, not having to solve a problem. Okay, so I hope that covers the motivation for using graphs. One of the reasons I like to do that is that I always think, I don't know if you're the same as me, but I have this tendency to just forget stuff if I don't think it's going to be useful to me. I can assure you graphs are going to be extremely useful to you in your career as a computer scientist. You're going to encounter them again and again and use them again and again. But yeah, it's important to know that so that you know what you're getting yourself into. Okay, so a lot of the graph chapter is fundamentally concerned with definitions. And, it's things like nodes are said to be adjacent if there is an edge between them or something, right? All the vertices that are adjacent to a vertex are known as its neighborhood, that sort of thing. And I see no reason for me to go through that in the lecture. That stuff's covered in sections 3.1 and 3.2 of the book. And you should just go and read that. And as I said in last week's lecture, I'll wait. Go read those and then hit pause again, and we'll move forward. So those sections were pretty dry, right? They probably weren't super interesting to you. You kind of have to know the terminology, so those were just covering the bases. But I hope you got through them without too much trouble. Obviously, if you have any questions about those, please post them on the WhatsApp group or the forum. On the forum, the tutors will probably handle the question, and if they don't, please let me know. And on WhatsApp, I'll handle the question, and if I don't, please let me know also. Okay, so what I want to talk about, which I think is actually kind of interesting, is how do we represent these graphs on a computer? So it's fine to say, we've got these nodes and edges or vertices and edges, and we're going to solve problems relating to them. But we're going to solve them by writing programs. And if we're going to solve them by writing programs, it's going to be important that those programs have some way of representing what this graph looks like. The first representation type I'm going to talk about is an adjacency matrix. Okay, it's called an adjacency matrix because what it stores in the matrix is whether two vertices are adjacent. Okay, so you end up with this, let's say you've got this graph that's drawn over here with vertices 0 through 5. That means we've got to have 0 through 5 on the for the columns and 0 through 5 for the rows, right? And what the items in the matrix will represent is whether those two vertices are adjacent. Okay, so if we look at column 0, row 1, right, we get this true. What that indicates is that there is an edge between vertex 0 and vertex 1. Okay, similarly, if we look at vertex 0 and vertex 2, we'll see there's no edge, so we end up with a false. 0 to 3, there is an edge, so it's true. 0 to 4, there is an edge, so it's true. And 0 to 5, there isn't an edge, so it's false. Okay, and that's as simple as it gets, right? So it's the same for column 1, column 2, column 3, column 4, column 5. The thing about this graph is that it's an undirected graph, right? You'll see there's no pointy arrows. The edge doesn't go from 0 to 1 or from 1 to 0. It goes in both directions, or in neither direction, I guess, considering we're using the term undirected. Now, for an undirected graph, if there's an edge between 0 and 1, there will also be an edge between 1 and 0, right? So that means that this matrix is going to be symmetrical about this diagonal. And I mean, that kind of makes sense because it's undirected, so the edges have to correspond, right? If the graph was directed, you'd find that this wouldn't necessarily be symmetrical. Okay, and a competing type is we have an adjacency list. And we'll generally be choosing, we either want to use an adjacency matrix or we want to use an adjacency list to represent our graph. And we don't really know until implementation time, right? So how an adjacency list works is that each vertex keeps a list, a linked list basically, but I mean, you can use any type of list. A list of its adjacencies, meaning of the vertices that it's next to. So if we look at vertex 0, it has items 1, 3, and 4 in it. What that means is vertex 0 has edges to 1, 3, and 4, and nothing else. Vertex 1 has edges to 0, 2, 3, 4, and 5. So 0, 2, 3, 4, and 5. Vertex 2 only has an edge to 1. So you'll see like it's a bit of a more complex, compact representation. But what it's saying is every vertex kind of keeps track of which vertices it's next to. Okay, so you've got these two representations, adjacency lists and adjacency matrices. And they fundamentally represent the same data. Okay, so this adjacency list and this adjacency matrix both represent this graph. Okay, so they're not doing anything different. Then the question that should be on your mind is, well, why do both of these representations exist? So in any field, if you have a technique that is dominant, meaning it's better than any other technique in all circumstances, other techniques will just disappear, right? There's fundamentally only one way to do a high jump, for instance, simply because it's the best way. Nobody bothers trying anything but what's called a Fosbury flop because it's just better. And so, you know, the same sort of thing should apply here. If an adjacency list is better, why does an adjacency matrix still exist? Why is it something we still talk about? And generally, when you find two methods that are still popular, it's because they're different in some way, but they're both good in different ways. Okay? So if we look at these two representations, let's say I wanted to check whether two vertices are next to each other, right? So whether maybe vertex 0 is adjacent to vertex 4 or something. If I want to do that using an adjacency matrix, I'll just look at 0, 4, and I'll see a true, and I'm done. Right, so that's a constant time operation. I just looked it up in the matrix and I said, well, it was either a true or a false, so I know that these two are adjacent. But what do I do in an adjacency list if I want to figure out if vertex 0 is adjacent to vertex 4? What I have to do is I have to go and look in vertex 0's linked list, or list, it doesn't have to be a linked list, and check if 4 is in there, which fundamentally means I'm doing a linear search. Right, I'm looking through vertex 0's list to see if vertex 4 is in there. Or in an undirected graph, I could look through vertex 4's adjacency list to see if 0 is in there. But either way, what I'm doing is a linear search, which in the worst case is theta n. Okay, so the adjacency matrix wins. So we're done, right? We don't need to care about adjacency lists. No, actually we do. And the reason we do is, let's say I wanted to check the degree of a vertex. So let's say I wanted to see how many vertices vertex 0 is next to. In an adjacency matrix, what I'd do is I'd go through and I'd count the number of trues, because each true represents an edge between 0 and something, right? So I'll go through it, I'll get 3, but I'll do that by counting. Okay. Here, what I do is, because lists tend to keep a representation of their size, I can just read the size as 3, which will take me 1, and I'm done. Okay. Similarly, if I wanted to iterate through all of the edges, which is a quite common thing to do in graph algorithms, maybe I'll say, starting from vertex 0, look at all of its edges and do something, right? To look at all of the edges using an adjacency list representation means just iterating through this list, which has 3 items in it. Okay. In the adjacency matrix, what I'd have to do is go through all the items and ignore the falses, which will obviously take longer, right? Because the falses that I have to ignore here just don't appear here. I don't even have to think about them. So the adjacency list wins in this case, or these cases. So the choice of which representation to use is dependent on what algorithm you're going to perform. There's some algorithms that are going to have to check for adjacency really often, in which case it's worth using an adjacency matrix. There's some that are going to have to iterate through the list of edges, and so you might want to use an adjacency list. Occasionally it might make sense to keep both representations so that you can keep both benefits. That does mean you'll have some cost in terms of space, right? Because you'll have to keep both representations. Okay, and that's pretty much all I wanted to talk about today, is representing these graphs. And why I wanted to talk about it, even though it's not a lecture session, is because that's what today's lab is about. So the code today has you implementing an adjacency list. This is a more important lab than it sounds, and although there are easier ways of doing the lab than actually implementing an adjacency list, you could, for instance, implement an adjacency matrix if you want. Next week's lab will use an adjacency list. So if you don't do this week's lab properly, then next week you're just going to have to do this week's lab in order to do next week's lab. So it's not worth trying to life hack your way through this one. Just do the lab as designed, and you'll save yourself a lot of effort. For the record, it's not just next week's lab. There's like 4 or 5 labs after this that all depend on this week's lab. So do it, understand it, and anything you don't understand, please ask the tutors, and ask me, and ask your classmates, because this is a quite helpful class. Okay. Thanks, everybody.